Hello, welcome back. In the previous few slices of physics, we have done problem solving with forces, and one of the forces was friction. Now we're going to take a deeper look at friction and understand first that it comes in two forms, static and kinetic. We're going to answer questions like which one of these forces is involved when an object is at rest, and what does it look like? Which force is involved when an object is moving, and what does it look like? What do these forces depend on? What are their magnitudes and directions? Let's take the example of a heavy box that's sitting on the floor, and my goal is to slide this box across the floor to get it to somewhere else. So in the first case, before I get started trying to push it, the box is just sitting there. What are the forces acting on this box in this state? Well, as we go around it, there's only one contact of the box, and that's with the floor. And we know that contacts can have two types of forces. I'll have a normal force that's perpendicular to the surface, so in this case that would act straight up. And the other contact force that I may have is friction, which is what we're going to discuss. Let's put that on hold for a second and confirm that there are no other contact forces with this box, so the only other non-contact force we have, as usual, is the weight. We also know that friction acts parallel to the surface, so in this case it would be horizontal. So there can't be any other vertical forces, and for this box to be in equilibrium along the y-axis or vertical axis, we would have to have n equals w in magnitude, but they're opposite in direction, so they'll cancel each other. If I did have a frictional force, let's say it acted to the right. There is no other horizontal force to counter that, so that would mean that this box would be accelerating to the right. And since it's not, it's just sitting there, I cannot have a frictional force to the right, and the same is true for a frictional force to the left or in any other direction for that matter, because if there was a frictional force with nothing else to counter it, the box would be accelerating in that direction, which it can't do just sitting on a horizontal floor. So we conclude that in this case, when the box is just sitting on the floor, the frictional force is simply zero. So now let's take the example of me pushing on the box. I'm starting to apply a horizontal force on it to the right, but I'm still not able to move it. The friction is stronger than my pushing effort. And let's take 3 examples as I intensify my effort of the pushing force on the box to the right. Let's say I push it with a force of 5 Newton. The box is not moving. Then I lean into it a little bit more and push it with a 10 Newton force. The box doesn't budge again. And I push it with a 15 Newton force, and the box is still at rest. So in all these cases, the box is not moving. That's the common factor. Let's see what the frictional force in all these cases has to be. I'm going to draw a partial free body diagram here and show only the forces along the horizontal or x-axis. And just for completeness, let me mark the x and y-axis over here. The reason I'm drawing a partial free body diagram here is that we already know that the normal force and weight are the only two forces along the y-axis, and they balance each other. And so rather than repeat that, let's just focus on friction, which is the topic of discussion, so we'll only draw the free body diagram along the x-axis. So in the first case, I've got a pushing force, let's call that Fp, of 5 Newton. For the box to be in equilibrium, which it is, the net force along x-axis has to be 0. And for the net force along x-axis to be 0, the frictional force acting on the box has to be 5 Newton to the left. Now when I lean in and push harder, I've doubled the force that I'm applying, so my Fp is now 10 Newton, but the box is still in equilibrium, so the frictional force has to grow to oppose the 10 Newton force that's applied so that the box remains in equilibrium. And then when I apply a 15 Newton force, working even harder, the frictional force once again has to grow to 15 Newton, otherwise the box would be accelerating, which it is not. All of these forces, when I have a condition when the box is not moving, are static frictional force. And the interesting thing about static frictional force is that its magnitude changes based on situation. And by the way, its direction also changes based on the situation, because if I started pushing it to the left, the frictional force would act to the right. It's always going to oppose the intended motion and be whatever magnitude and whatever direction it needs to be to prevent motion. But it can't do that forever. We know that we can slide the box down the floor if we work hard enough. So this Fs has a maximum value. So the magnitude is limited to a max value. And that max value is called Fs, max. And that maximum value depends on two things. It depends on coefficient of static friction, and it depends on the normal force. The first term here, the coefficient of static friction, depends on the materials. You know that it's easier to push a block of ice on an ice floor than it is a rough wooden box on a rough wooden floor. So that is captured by the coefficient of static friction, and it's just got a constant number value, and it's unitless. N is our usual normal force. Okay, let's move on to this third scenario where you're pushing on the box and you are able to move it. So now, let's say you are pushing it with a 20 Newton force. When you push it with that force, not only are you moving the box to the right, but you are actually accelerating it to the right, speeding it up. So in this case, my pushing force is 20 Newton. My frictional force has to be something less than 20 Newton. Let's say it's 16 Newton. I'll explain how that comes in a little bit. Okay, now that I've got the box going, I don't want it to keep speeding up across the floor, so I ease up my force and bring my pushing force down to 16 Newton, and that matches the frictional force of 16 Newton, and so now this box is in equilibrium. The net X force is 0. But when a box is in equilibrium, that doesn't mean that it's at rest. It just means that the acceleration is 0. And in this case, because it was already sliding to the right, it's going to keep doing that at a constant speed. And once I approach my destination, I want to slow the box down to a stop. The frictional force is still 16 Newton. And my pushing force, maybe I dropped it down to 7 Newton. And that would cause the box to accelerate to the left. And because the box is moving to the right, accelerating to the left would slow it down, helping me bring it to a stop. So all of these scenarios, while the box is moving, whether it is speeding up, maintaining the same speed, or slowing down, the frictional force is called the kinetic frictional force. And the kinetic frictional force is an easier thing to work with than static friction because this has got a fixed magnitude as long as the object is moving. And if it's not moving, this is irrelevant. The frictional force would be static frictional force. And the magnitude that it always has as long as the object is moving is mu k times n. Now you will know from practical experience that it's easier to keep the box moving than it was to get it going at first. So this mu k is also just a constant that depends on the materials, but mu k is always less than mu s for the same set of materials, and n once again is just a normal force. So in this example, my Fk was always 16 Newton, and its direction is always opposite the direction of motion, and since I'm moving to the right, it's going to be pointing to the left. One surprising thing with the kinetic friction is that it's independent of the speed or the acceleration. All it cares about is that is the object moving or not, and if the object is moving, you will have this mu k times n amount of kinetic friction, and its direction will be opposite the direction of motion. Another surprising thing is that static and kinetic friction do not depend on the surface area of contact between objects. So if you had a wide base or a skinny base, the frictional force will be the same. It only depends on the materials, and it depends on the normal force. And finally, here are some example values of mu s and mu k that I've given you, the coefficients of static friction and kinetic friction. Remember, mu s controls the maximum static friction, mu k controls the kinetic friction, the constant value of kinetic friction. And as you expect, different materials have different values. So rubber on concrete is a lot stickier than wood on wood or ice on ice. So the coefficient goes from 1 to 0.5 to 0.1. And the same trend is seen for kinetic friction. And then the other trend you see is that the kinetic coefficient is always less than the static coefficient because things are stickier when they are at rest than when they are already in motion. So a lot of concepts discussed in relation to static and kinetic friction. So let's recap real quick. Static friction, which we call F subscript S, applies when an object is at rest, and its magnitude changes. That's the most important thing to remember. It depends on the situation, and it can range between 0 and a maximum value, and that maximum value is given by Fs max, which depends on the coefficient of static friction, which is a function of the two materials in contact, and the normal force. It's a product of those two things. Its magnitude and direction adjust to whatever they need to prevent motion up to a certain point, up to that maximum value. Kinetic friction is the simpler thing. We call that F sub k, and it's simpler because its magnitude is always fixed at a constant value of Fk as long as the object is moving, and that Fk is mu k times n, where mu k is the coefficient of kinetic friction. It's a number that's always smaller than the static coefficient for the same set of materials, and it depends on normal force. The direction of kinetic friction is opposite the direction of motion. And the Fs max and Fk depend on the two things we discussed, the coefficients of friction and the normal force, but surprisingly they do not depend on the surface area of contact, the speed of the motion, or the acceleration of the motion. Thank you, and in the next video we'll take an example problem to look at these concepts.